Hello and welcome back to another video on microprocessors. In this video, we are going to be discussing how to interface memory devices to a processor. But before you can actually interface a memory device to a processor, you need certain peripheral devices, interfacing devices in between. They are the go-between between the processor and the memory chips actually. So what are these kinds of devices? The first one is called a decoder. And the decoder that I am going to be talking about is called the 74LS138. It's a 1 of 8 decoder. What it really means is that this particular device has 8 active outputs, and at any point in time only one of them is active. It takes 3 inputs, decodes them and gives you an output at one of the 8 output pins. Typically a decoder is a device that takes n inputs and gives you 2 to the power n outputs, and at any time one of the 2 to the power n outputs is active. In the case of the 74LS138, let's first understand what this number stands for, right? The LS stands for low power Schottky, and low power Schottky is the technology used to make such ICs, and it is a high speed device. And what does this high speed means? It means the transition time between an input change and an output change. It's called the latency of this device. The 74LS is the series itself are typically low power Schottky series. The 138 is a 1 of 8 decoder. How does this particular device work? It takes 3 input pins, in this case the address lines A0, A1 and A2, and these 3 address lines are decoded to 1 of 8 output pins. In addition, the 74LS138 is unique in that it has got 3 enable pins. They are called E1 bar, E2 bar and E3. The reason the designers have given you 3 enable pins is that you can now cascade and use multiple 74LS138s in your design, and based on the choice of E1 bar, E2 bar and E3, one or the other of the 138s gets selected. The way to look at this from a truth table perspective is really what I am now showing you on the screen. As long as the E1 bar, the E2 bar and the E3 are not at either active low or active high, the output is tri-stated. You cannot use any of the outputs. The moment E1 bar and E2 bar are low and E3 is high, the chip is enabled. Then based on the values of A0, A1 and A2, one of the 8 output pins goes low. This is the way a decoder works. The next device that you need to interface with memory chips is what's called a latch. Why do you need a latch? Remember that the 8086 multiplexes the data and the address lines. So when the address line is active as an address bus, you need to latch the address value, and you use a latch to latch the address value. The 74LS373 is an octal transparent latch. Octal meaning there are 8 latches built into one chip. It is transparent because of the logic used in the 373. How does this work? The moment the output enable is low, whatever you see on the input pin is available and visible on the output pin. That means the input is transparently available on the output. If the output enable pin is high, then the output of the latch is a tri-state condition, high impedance condition. If the output enable is low and the latch enable signal is low, then the output is latched to the previous state of the input signal, and after that the output will not change its state as long as the latch enable continues to remain low. So it has latched the input value onto the output pin. Let's look at a different device now. This is called a flip-flop. So we spoke about decoders, we spoke about transparent latches. The third device is called a D-type flip-flop, and this is also an octal device. That means 8 flip-flops in one chip. You should be asking yourself, why do they have 8 in these chips? And the reason is a data bus or an address line bus is typically 8 bits long, 16 bits long, so on and so forth. So if you have an 8-bit bus, one chip, you got 16-bit bus, you need 2 chips. So it makes the design much simpler. This particular flip-flop is called the 74LS374. Now, how does this particular flip-flop work? So in contrast to the latch, this is an edge-triggered device. So the output enable must be low, so it is OE bar. So the output enable signal must be low. The output gets latched to the input state on the rising edge of latch enable. So from low to high, when the latch enable signal goes from low to high, whatever was on the input pin gets latched onto the output pin and it will remain there till you decide to change it again. So the difference between a D-type flip-flop and a transparent latch is, in the transparent latch it was a level enabled latch, this is a edge triggered latch. The last device you would need to interface processors is something called the transceiver, the 74LS245. The transceiver is a transmitter receiver, and in this case again it is octal, so there are 8 transmitters and receivers in one chip. Why do you need transceivers? Typically for the data bus, because the processor can write data to a memory or it can read data from a memory. And it is a non-inverting transceiver, and that's good because you obviously whatever is seen on the microprocessor pin must be seen on the memory pins, whatever is seen on the memory pins must be seen on the microprocessor pin. So it is a non-inverting transceiver. How does this work? If you look at the internal circuitry of the 245, the 74LS245, you have got what is called a direction pin. If the direction pin signal is high, whatever is at the input pins A1, A2, etc. will be visible at the output pins B1, B2, B3. If the direction pin is low, whatever is at B1, B2, B3 will become visible at A1, A2, A3, and that's how the direction pin can be used to configure the direction of data movement between the A pins and the B pins of the 74LS245. When do you use these devices? Now, decoder is pretty simple, right? So outputs of decoders are used to select one of multiple chips, and a typical decoder is giving you 8 output enable pins. So you could connect 8 devices to one decoder. Based on the values of the address lines, one of the 8 chips gets selected. Without the decoder logic, you would have to do this independently as a designer, and you would have to build complex decoding logic to select one of the multiple devices on a typical system. A latch, as I mentioned earlier, because the processor multiplexes the data and address lines, you need a latch to ensure that you have latched the address lines till the memory device or the memory chip has consumed that information. And the transceiver is to buffer multiple devices from the processor. Otherwise, it is possible that more than one device is suddenly generating information on the data bus, and then the processor does not know which device it is reading from. So typically, these are the kinds of devices you will need to interface a memory chip to the microprocessor. Obviously, there are very many kinds of latches, transceivers and D-type flip-flops. I would urge you to read up a little bit more on these kinds of devices, because only if you are clear about the construction of these devices, the design of these devices, will you be comfortable in using them in circuits. In our next video, we are going to be looking at the details of memory architectures and what kinds of architectures are typically used in PCs, in computers of any kind, so on and so forth, and how you can enable them using the devices that we have just seen. Till then, happy reading about peripheral devices. Thank you.